So in the last video, we were able to estimate the area, and we got, depending on how you count it, either roughly 0.4 or 0.2, or if we average those, somewhere around 0.3. And now we want to transition towards finding the precise area. And so the key idea here is that you study what happens to your area estimate as the number of rectangles in, I'm going to imagine having n rectangles, as the number of rectangles goes to infinity. In other words, you take a limit. You just take the limit of your estimation as the number of rectangles goes to infinity, and somehow that makes sense. If we scroll back up and I just make these rectangles finer and finer and finer, more and more and more and more rectangles, then my area estimation is going to get closer and closer and closer to the actual value, and hopefully that's something we can compute. So for this specific example, this is not something we'll always need, but in this example, I need to remind you of a little formula you learned in discrete. So if you add up the first n squares, so 1 squared plus 2 squared plus 3 squared, and you keep going and you stop at some number n, then this is actually equal to n plus 1 over 2n plus 1 all over 6. Just in case this is not something you remember, let me just show you. So let's say 1 squared plus 2 squared plus 3 squared. I stopped at 3, so that's my n. So this should be 3 times 4 times 7 over 6. This should be 14, and then you check, and let's see, 1 squared is 1, plus 4 plus 9, look at that, it is 14. So it works. So just keep that in your back pocket. We're going to need that in a minute to work out our problem. Okay, so here we go. We need to somehow, we need to somehow write down an area estimation, not using 4 or 5 or 200 rectangles, but using an arbitrary n rectangle. So let's first compute delta x. Delta x is you take your b out here, this is 1 to 0, you take b minus a, so 1 minus 0 over the number of rectangles, so over n. So delta x, the width of each little piece down here, is going to be 1 over n. And now we can break up our chunk of x-axis into little intervals. So we're going to go from 0 to 1 over n, and then over to 2 over n, and then to 3 over n. And then we're just going to keep doing this, and then we're going to get to n minus 1 over n. And then finally, we're going to view 1 as n over n, which is 1 itself. So that's how you break it up with n rectangles instead of 4 rectangles. And now you can pick, it doesn't matter if you pick left endpoints, right endpoints, midpoints. Let's just do right endpoints. Let's write down the right endpoint estimate with n rectangles. So r sub n, not r sub 4, r sub n now. We're going to take the right endpoint of this first interval, and we want to compute the area actually of this rectangle. So that area is going to be, well, it's going to be the width 1 over n times f of, plug in the right endpoint, plug in 1 over n, plus the next rectangle is going to be this one. Width is 1 over n. Height, plug in 2 over n. So f of 2 over n. Let's do the next one. So this is the rectangle. Width is 1 over n. And then height is, plug in the right end. Whoops, not that. That's the eraser. Plug in 3 over n. So f of 3 over n. And then you just keep going, and then we're just going to say dot, 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 and you're going to get to this last one right here, and you're going to say, okay, actually, let's do this one. So there's really a rectangle right here where this is the right endpoint. So you're going to get a 1 over n f of n minus 1 over n, plus the last one is 1 over n times plug in 1. But let's just say, let's still write it as f of n over n just for completeness sake. All right, so now we're going to factor that 1 over n out. Each one of these has a 1 over n in it, so we're going to pop that out, and then we're left with f of 1 over n plus f of 2 over n plus f of 3 over n plus da-da-da-da-da, f of n minus 1 over n plus f of n over n. And now we know what f is. F is x squared, so I get 1 over n. I get 1 over n squared plus 2 over n squared plus, 2 squared over n squared, 3 squared over n squared plus n minus 1 squared over n squared plus n squared over n squared. All right. And now I'm going to say, oh, look, each one of these has an n squared downstairs. So let's factor that out as well. And we can write this as 1 over n cubed. And then I'm going to think about 1 as 1 squared, because it is. 2 squared plus 3 squared plus n minus, I should put some dots here, otherwise that's not true, plus n minus 1 squared plus n squared. Oh my goodness, that's the formula that we just looked at right there. So I know how to simplify that. So this becomes, let's see here, this becomes 1 over n cubed times, this whole thing simplifies down to n times n plus 1 times 2n plus 1 all over 6. And you learned this back in discrete. Like I said, you can look back at your notes there. So let's cancel one of these n's and simplify this. And so we get n plus 1 over 2n plus 1 over 6n squared. And so you need to realize that we actually have a really nice formula for the estimate of using n rectangles. So r sub n is n plus 1, 2n plus 1 over 6n squared. And so the point is, we can get our hands now on, hey, what happens if you use 4 rectangles? And you're going to get 5 times 9, right, over, let's see, 16 times 6. I'm just going to say 6 times 16. And you can approximate this, and we're going to get, let's see, 45 divided by, oops, hold on here. 96, and I get, this is roughly 0.46875. You could estimate with R100 now, with 100 rectangles, and you're going to get 101, 201 over 6 times 100 squared, and I'm not going to estimate it, but the point is, you can actually, you can estimate the area as accurately as you want, but that's actually not the point. We're not interested in estimating it anymore. We want to get the precise area, and so here's what we do. We need to realize that the area that we're after is equal to the limit as n goes to infinity. Oh yeah, we're not done with limits yet. Of r sub n. Well, this is the limit as n goes to infinity of n plus 1 over 2n plus 1 over 6n squared. And you could work this limit out using L'Hopital's rule. I'm going to do it the old way, where we just divide out by the highest power of the variable downstairs. And so I'm actually going to expand. Let me rewrite this. I'm going to expand the numerator out and write this as 2n squared plus 3n plus 1 over 6n squared. Let's actually move this guy downstairs. There we go. And so I get the limit as n goes to infinity of 2 plus 3 over n plus 1 over n squared over 6. As n goes to infinity, this goes to 0, this goes to 0, and so I'm left with 2 over 6, which is 1/3. And so the conclusion, here we go, the area, the precise area under x squared between 0 and 1 is precisely 1/3. And so that's it. We got our hands on the exact area using limits. And so we're going to be able to write this down, this process down in a succinct kind of way. But I hope, after seeing how tedious and technical this is, I hope that you're motivated to develop some theory and some tools to make these computations easier, so that you don't have to write down these interesting sums and try to take these strange limits. So that's where we're going. I need to write down some things, and then we're going to, in the next lecture, we're going to be able to develop some theory. So next video, let's write down what's actually happening and then some properties.